We are very happy to have Atakan today. He's going to tell us about topological recursion for hyperbolic string field theory. Yeah, we start. You roughly have about an hour and a half.
Okay, first of all, thank you for the organizers to invite me again. The last time I enjoyed giving a talk in ICTS online, and I hope we are going to enjoy this time too. But yeah, today I'm going to talk about my work with Nico, who's a brilliant grad student at MIT, and here's the number. And here's the date, although it's like it's 2nd of October here. So anyway, basically, let me start with by giving the goal of this work, eventual, like why we do this. So we basically want to solve closed string field theory equation of motion. So this is of course, this is a heroic task. And like a priori, it's not obvious how to do it. Like this is basically some non-polynomial equation. And you're asking like if somebody hands you up some like random function, can you find its zeros? So it is not like a priori obvious to how to do this. So the one thing that you can hope for is that basically certain relations between these interactions. So let me begin by telling what these are. So this is basically your free term, and these are your interactions. So as I said, and there are like an infinitely many of them. So what one hopes to do is that to basically find relations between them. Somehow knowing the first one will tell you the second, this order, and the next and the next. So that's the overall goal here. And what we show with Nico was that we show that these higher interactions, like quartic, quintic, etc., can be recursively found given some generalized cubic vertex in this particular SFT where you use very particular set of field parameterizations. So that's our main result. And then the eventual goal is, as I said, apply this what we find to actually like construct solutions. So before I do that, let me explain like what closed string field theory is. So sorry for the expert giving this introduction again, but I'm told that I should give it. So, okay, let me start with a whole SFT business. Well, basic idea is that it is some reverse engineered field theory. So it's reverse engineered from on-shell string amplitudes in the following way. So basically the whole prescription of the on-shell string amplitudes is that you take some moduli space of Riemann surfaces. I will call them MGN. And then you basically integrate over CFT correlators determined by some 2D CFT with BC ghosts and the matter sector. So I'm going to talk about Bolognese one, so C equals 26 for the matter. And then you generate the on-shell string amplitudes. So that's the usual prescription. So what we want to do in string field theory is that we want to find a field theory whose on-shell amplitudes will be same as these ones. So in order to do that, we need a notion of off-shellness. So the way you do it is that you're basically going to endow this MGN with some extra structure, and then you're going to use similar same CFT to the map to find off-shell string amplitudes. And by doing this choice wisely, you can actually get from this off-shell amplitudes, you can get some field theory. But this is the basic idea. We are just basically putting more like unphysical parameterization to achieve off-shell amplitudes and later try to read a string field theory out. And as I will tell you, like there is a huge amount of redundancy and unphysical degrees of freedom here. But nonetheless, they are really important to find vacuums, like because or like doing stuff like renormalization or vacuum shifts. So these are essential things to have in your theory. Okay, so let me talk more about this extra structure. So here's the some on-shell amplitude. So it's AGN, and I'm computing between these on-shell fields for now. Well, the way you do it is that, again, some modular integration with some CFD correlator in a particular surface. So there are some B-ghost insertions, which I will talk eventually more about that. And then there are states that you insert. So as I said, the extra structure is about making sure these things are also defined off shell. So here, if these are on shell, then QB psi 0, and actually you can choose a psi 0, primary as your representative. Also, there's this equivalence. So you can choose this. And if you do that, then this particular integral can be done on the surface directly. You just put this vertex operators wherever you want, and then you integrate over them, and you get the on-shell amplitude. The problem here is that for off-shell, this condition is no longer true. So then, in general, they are not 0, 0 primary. So what will happen is that you need to supplement this amplitude with extra data so that you can also keep track of them. And in string field or in general off-shell amplitudes, the way we do it is basically when we put the operator in somewhere in the surface, we are actually not putting directly, but we are actually putting into this unit disk first, then we are mapping to the surface in a one particular way. So here it's denoted by like this. And then the B-ghosts are going to get modified according to this, and your integration is also going to get modified. So this is the basic prescription to compute off-shell amplitudes. Like basically you need to choose not just Riemann surfaces, not just complex structures on 2D surfaces, but also local coordinate choices around the punctures. So this is the extra structure that I was talking about. Okay. Well, as I said, we want these off-shell amplitudes to come from some sort of field theory, though. And the way this will work is that you want to decompose these amplitudes so that you can interpret this as a bunch of vertices connected with a propagator. And the natural notion of propagator in string field theory is this one. Basically, it's a flat cylinder of some length S and some twist theta. And these are the natural ranges. And you basically construct the Feynman diagrams like this, given like this surface, for example, and this surface, and identifying their local coordinates like this. So it will create this flat cylinder. And then you can, for example, this total surface is genus 2 with one puncture, this whole thing. And you are able to write the amplitude associated with this, with these two vertices and a propagator. This will be one contribution. But here's the challenge, or fortunate, unfortunate, I don't know how you interpret it. Not every Riemann surface can be constructed this way. So say you want to construct a 4-puncture sphere. You might imagine I take 2-puncture sphere and create this propagator. Well, it turns out you cannot cover entire moduli space. You can just cover parts of it, and there will be gaps remaining, and those gaps are representing surfaces that you cannot construct as Feynman diagrams. Those are going to be elementary vertices of the theory that you're talking about. So these are called string vertices. So these are basically the way I'm going to write this is like this. So yes, is there a question? It appears not.
I don't think so.
By the way, you can interrupt me in a second. Like it's okay. So okay, so this is the way I'm going to write is like this. So this VGN is that, like I said, these are the surfaces that you can not construct with propagators. So these are like some Riemann surfaces with choice of local coordinates. Then I collect them as like this formal sum, where I put some Planck's constant and string coupling to make the counting easier. And I sum over the GNN and with these constraints. Well, the one thing that you should notice here is that these are all hyperbolic surfaces. So, which I will call stable, because it's a common way to write these sums. And I'm going to represent all of these vertices as this like a particular sum. So these are the objects that describe the interactions.
So the VPNs are the contact interactions, right?
That's correct. Yeah. Those are elementary interactions. I wouldn't say contact interactions, but yeah.
Okay, but like the direct 4-point vertex or the direct 5-point vertex.
Yeah, that's correct. Yes. So these are literally, this, etc. Yeah, the contact for me means a very particular parameterization, so that's why I try to avoid using it. But anyway, you are right. Anyway, so these are these are going to be the objects that you use to construct those square brackets that I showed at the beginning. Well, these are not, okay, there's huge redundancy in this, but they're not totally arbitrary. They obey something called geometric master equation, which is, this thing. I will explain why this is so crucial to construction of string field theory soon. But, one thing that you immediately notice is this is just some recursion relation. So it's not going to be the R recursion relation, but it's a recursion relation that has to be imposed initially. So basically, you take these sum and you just put it there. And these operations are multilinear, as I will describe. And you get this like this order by order recursion. So, for example, in 4-puncture sphere, this is a 1-puncture torus, this is it, and a 5-puncture sphere is that one. But let me go to like this, the other order, like the next order. So say that it's a 2-puncture, one genus torus. So this equation tells you the following. So you say that, okay, these are some sets. And for example, if your surface is in this set, by the way, this operation is called anti-bracket. And this is called Laplacian. And the way they are defined is essentially that you're taking surfaces, they're defined on the sets, on the string vertices, and they are defined in a way that you're taking surfaces from here, you're taking surfaces from here, and then you're identifying them with the collapse propagator. So instead of like having full propagator, you say that the S equals 0. And then you construct all possible surfaces this way. Like, for example, here, this was a 1-puncture torus, this was a 3-puncture sphere. And then for like their coordinates, like the coordinate of here and one of the coordinates here, you identify with this collapse propagator. And this surface is going to be belonging to here. And similarly, Laplacian is a similar type of operation, but instead of solving 2 different surfaces, you are self-solving the surface. So for example, if you solve a 4-puncture sphere, it will generate some genus 1 2-puncture surface. So, and this
Hello.
one is the, yes.
Oh yeah, so my question was, so these operations basically, so they define the intersection of the surfaces, right?
well, I wouldn't call it intersection, but rather they are like creating new surfaces from the lower, like higher order surfaces from the lower order surfaces.
Okay.
Yeah, so intersection in the sense that like, yeah, you imagine these are border surfaces, then yeah, you are identifying borders. If that's what you mean by intersection, that's correct.
Yes, that is what I meant, Professor. Thank you.
Yeah, okay, then it's fair. Yeah. So
sorry, one more question. So the del refers to a derivative on the coordinates of the moduli space. It's essentially, right, from the boundary of moduli space.
Yeah, I was going to just mention that. So you see, these are I was calling them set, but technically they are chains, and this del is essentially the boundary operator acting on these chains.
Okay.
So yeah, yes.
And I should think of this, I mean, I'm just trying to operationally understand this equation. So I should think of this, okay, these V's are some chains in the, or maybe you will explain and then I will ask a question. Okay.
Exactly. I scroll down to like just explain this because yeah, so this VGNs, you should think they are living in this particular bundle. So this is a moduli space of Riemann surfaces. And this is when you put the local coordinates. So, you know, like you have one surface, but you have many choices for the local coordinates, which forms a fiber. And this VGNs are essentially some chains on this bundle. You know, usually people want it to be sections, but it can be anything that you can do some integration. So there are some singular chains, and this equation, you know, for this one or the general one, essentially tells you that the boundary of this chain is the same as when the Feynman diagrams will collapse. It's the same as what you will get when the Feynman diagrams will collapse. So this is the notion that we are talking about. I think I cannot hear you.
Sorry, it's locally true in the sense that it is that corresponding to every such section or every such chain, there is I mean, so on the left-hand side, you have del V, the boundary of that chain, and that's equal to a corresponding set of corresponding section of the other the lower genus ones. Is that yeah?
So, you know, you can think this as a recursively, you know, say that you choose some three-puncture sphere, which is just, there is one. Like this is just a like point, right? The moduli space is a point, and the fibers are choice of local coordinates. But you need to choose one, which is just a V03. But then you do a operation to get the M04. And there's a P04. Right? And you create Feynman diagrams using this one. And these creates these Feynman diagrams. So, and this point is lit V03, V03, and this one as well. But then what you need to do is that you need to fill the gap by some V04. Essentially, this means that like you construct some Feynman diagrams, but that doesn't like construct this chain, like this continuous chains that kind of covers MGN. And you need to put something like some V04 that will basically interpolate between them. And in this sense, this equation is actually kind of boundary condition. Is that satisfactory or?
I think I understood it, except of course when here it was a point, so there wasn't, it was kind of canonical, but when you have lower genus vertices which also have their own kind of they are like a section, then you're assigning you're saying for every V there must be some lower dimensional vertices which kind of can be glued up to give you that boundary. Is that how
so
I understand it? Yeah.
these are not points. So like the VGN has dimensions 6G minus 6 plus 2N. So it's the same as the modular space's dimension. And so DVGN is the one lower.
Yes.
So basically, if you just consider these things, it's just codimension one.
Right.
And basically the ones that you construct in the lower ones, you see like I attach the border, right? But there's a still possibility of twist. Make sure like when you do the counting, right, you will see that like they are the same dimension and they should match.
Okay.
As a set, like they are the same sets.
So the set kind of the sum of the two terms will cover the whole of the boundary.
Yeah. So there's this minus sign, and that minus sign was about orientation. So you approach from this side versus this side, and they differ orientate, like they are different orientation. So as a chain, when you add up, you should get an empty set.
Okay.
As sets, they are the same.
So that's like, I guess, mathematically just what you said earlier, that these V's are covering the whole moduli space. So the other ones are kind of coming from the gluing of.
Yeah. So V's are partially, so they are like, you should think that instead of MGN, we are using this V's, but the crucial property that we want in string filter is that they are far from, like they don't contain degenerating surfaces. So if you go here, say that you create like a noded surfaces, what we want to do is that we want to describe them with Feynman diagrams where surface degenerates, we want to imagine there is a propagator. So that's why we are doing this construction.
Okay, thanks.
I hope it was clear. The basic idea of this equation is essentially providing this like the decomposition in a consistent manner. Like you construct Feynman diagrams, there are gaps, then you need to put something extra, and the way you put it extra is that you don't jump here. You put it in a way that everything is continuous.
Actually, I had another question. So like we do have a boundary operator over here. So like, is that correct? So this boundary operator basically in the context of the Feynman diagrams, like I'm trying to understand it in a way overall. So these Feynman diagrams, how do these interact with the, the moduli spaces? Like, for example, we have M03 and all. So like, how does this affect the formulation of the interactions between various surfaces and particles? That was my question.
Good. So again, like as I emphasized, this is like some off-shelf choice. So the different choices that you can make for V0, like the solution to this equation will define different string field theories, but it turns out those field theories are actually equivalent to each other. You can find a fielder definition in your path integral that will basically generate like changing an integration variable from x to x prime. It eventually reduces to that. So any physical observable that you will find from this theory, like whether it's on shell amplitudes or vacuums or whatever, should remain the same. So observables stays the same, but the way you construct them will differ. And that's actually a very good point, because again, any choice will work, but as I'm trying to emphasize, like if one particular choice is maybe better than the other ones in terms of like the way this decomposition is done. Is it
okay?
Is it good?
Yeah, that's fine for me, I guess.
Yeah. Okay. Good. Yeah. So this is a game we play. We are my favorite word for string field theory is reverse engineer theory. Like we are trying to generate a field theory from amplitudes. And like this is the one particular step where we decompose the parts of the amplitude so that we can interpret as a vertices versus genuine Feynman diagrams. Okay, so basic idea is then reduces the string vertices. Then you use the 2D CFT and then you get the SFT. So here's the so-called master action. So this one was free term. Basically, this is like there to generate these propagators if you do the gauge fixing. So this is its equation of motion. And when you gauge fix it, you generate the propagator. And the string vertices essentially becomes part of the interaction. So these are the interactions. So, and the way the important point here, these are like some, cubic terms, quartic terms, what have you. And like these are constructed by this integration now. So you see like instead of MGN, I'm using the string vertices. So this is the surface state. Basically, this contains the local coordinate choice that you make. There are some surfaces in here in string vertices, and the sigma GN varies that basically path integral over those surfaces. And there's a B-ghost insertion, and this is there to make it whole expression a differential form. Right? Differential form. And that will provide the B-ghost insertions eventually. And then if you write this theory, then you construct these Feynman diagrams and you consider these elementary interactions and you compute the amplitude and you put the on-shell state, you generate the on-shell amplitudes. So this is the whole construction. So so far so good, but let me explain why I impose this geometric master equation. Well, there are essentially two reasons. One is that you can use you use string vertices to construct this integration contour for your off-shell amplitudes. So you have vertices. So you have like one propagator Feynman diagram. And same as like 3G, like everything, the thing that you construct with cubic vertices plus propagator. So basically, you construct all possible Feynman diagrams and the vertices for genus G with M punctures. So one thing is that if VGN satisfy that geometric master equation that I told you, you can show that, okay, there are some big words here. When you push forward this to under this pi, which is forgetting the local coordinates, you want to have this as a homology class with the same as MGN. Basically, this geometric master equation implies this particular relation. And that means the following. If you take psi on shell, you can basically forget about anything about local coordinates and you will have generated the on-shell amplitudes correctly. So this is a one result, and that's what we wanted to have in the first place. And the other one is that the basic is somewhat related, is that if you satisfy this particular equation, then your master action solves the BV master equation. So its form is this. So I'm not going to talk about this very much, but the reason that you want this equation is that when you write a path integral based on this master action, and if you satisfy this particular equation, you can show that the path integral that you write is independent of your gauge fixing condition. So these are all we need, and these are all following from the master equation, the geometric master equation. So essentially, this is all, you find a solution to that equation, and you have a very streamlined process to define string field theory. So I think it's a good, next I'm going to talk about very particular solution, my favorite solution to this equation. But before I do that, is there any questions about the construction?
Yes, I do have one actually. So the master action basically in the theory, how does that relate to the sum over the genus and the vertex interaction? Like basically, what is the dependency of the master action on the vertex interactions?
So basically, master action contains this type of interaction between the string fields. Okay, and you say that you have n string fields, which is basically strings coming in, and basically when you have a string vertex, and you basically describe how these fields, how these strings interacting with each other. And if you expand strings in some basis to describe target space fields, so you say that you tachyons, gravitons, whatever, then you basically put it there and you evaluate this correlate the 2D CFT correlation function, and then it describes the various interaction between target space fields. So that's how it relates to the interactions, if that's your question.
Oh yeah, that was my question. And I also have another follow-up. So basically,
Yes.
what roles do the string vertices, like we have VGN? So what do these do? Like what is their role in basically constructing like non-perturbative solutions in this field of equations? Like
So
I guess mine. Yeah.
So there are two things here. As I said, these VGNs are essentially our choice. As long as we satisfy, solve this consistency equation, any solution will work. So they are essentially parameterizing the interactions. Like I said, it's just a dummy variable in the particular sense. So the way it will appear in the equation of motion later on is going to be, since it determines the particular filter variable, it will affect the particular equation of motion that you will get. And then you can get a particular solution to the equation of motion, and these are all dependent on string vertices. But what will happen is that if you try to compute something observable, say you have a solution and you want to compute its like a spectrum around that particular solution, that will be independent of the VGN. So basically the way we do it is that this is like coordinate choice, if you will, and you want to put a good coordinate system in your field configurations, basically. Again, you shouldn't understand these are really fundamental objects. They are not physical choices. They are just there to make our life easier. Good?
Yeah, that's good actually.
Okay, good. So yeah, don't overthink it, but still, I don't want to use, I don't want to use like a Cartesian coordinates for some cylinder problem, that doesn't make any sense to me. So it's the situation that we are here. Like I said, our goal was that doing this all order investigation, either for solutions or maybe non-perturbative stuff, then you need to be a little smarter about it, a little bit more insightful about it, how you do this all order construction. So that brings my that brings my favorite vertices, and those are hyperbolic ones. So as I said, the string vertices are all hyperbolic Riemann surfaces. So you might imagine let's put a hyperbolic metric on it, because I know it exists. This hyperbolic metric is a constant negative curvature metrics on the 2D surfaces, which is I take it in this units. I can put them always there in this uniformization theorem. So and you can build solutions to the geometric master equation. So this is done in this paper by Costello and Zwiebach. And let me explain the basic construction. So what you do is the following. You start with a bordered Riemann surface. Here I consider genus tree one bordered surface with the border length L1. You consider all those surfaces, but with the constraint that your systole is greater than some threshold length L. So this is threshold, I mean, cutoff length, threshold length. This is what we say. And the systole is that the length of the shortest non-contractible geodesic. So that means that if your geodesics, closed geodesics, non-contractible closed geodesic always have greater length than this L. And after you do this, you basically graph this cylinder, because I want to talk about punctured Riemann surfaces, not bordered one. So you just put it this flat cylinder, and that defines the local coordinate, because this is conformal to punctured disk. So it gives the picture that I showed you at the beginning. And then these are the so-called systolic subsets. So why these systole conditions are nice, and like usually how we go about defining string vertices? Well, the reason is that, as I said, there was this anti-bracket and Laplacian operations, which has a very particular geometric meaning. And that was like basically your flat cylinders has a collapse length. That was the interpretation. Now with systole condition, we actually can give a meaning to boundary operation as well. So boundary of this set will basically when the systole of the surface equals to L. Now we also have a geometric way of understanding of this boundary operator. And that will allow us to solve this geometric master equation.
Sorry, Atakan, so the systole being bigger than L is somehow ensuring that you don't have these long cylinders in your surface, right?
That's correct. Yeah, like if you don't have this condition, your geodesic can get arbitrarily small, and it can become a node.
And I want to the part of the tube perpendicular sort of the geodesic will be becoming very big.
Yeah, that's the right picture that you have. Like I will show it more. Like so, you see these surfaces in general are some mixed metric, right? It's like partially hyperbolic, partially flat. So like these are like around the punctures is always flat, but as you change the moduli, some geodesic can shrink to this length L, and once that shrinks, you will open a flat cylinder. So that's basically geometric understanding of what's going on. And like that's basically give this like a transition from the collapse cylinders, like you collapse the cylinder, then you increase the geodesic length. So that will give you a continuous transition.
And I just had a question about the notation. So the LIs correspond to the lengths of the boundaries around each of these punctures, right? There are borders, and of course you want all the LIs to be greater than this L, presumably.
Not yet. So for string vertices, actually, I will take Li to be L, all of them to be the same as this threshold length. For our construction.
At the moment, it is arbitrary, but greater than or equal to L.
No, it can actually be smaller. It doesn't matter. So, okay, there was another condition. Thanks for pointing out. Non-contractible, non-homotopic the border. So I only consider internal for geodesics. That's a really good question. Sorry, I overlooked this. So when LIs can be smaller than L, and because my definition for systole actually doesn't include the borders themselves.
Okay, thanks.
So that's the actual correct definition. Yeah. So, but otherwise it can be arbitrarily, but it doesn't mean they're always non-empty. If you choose your systole too high, and your border length too small, then it can be 0. Like the best example that I own is this genus 2 Bolza surface, which has the maximal systole in the genus 2 surfaces. So which doesn't have border in that case, but then you can still place a systole condition. And if you put the systole condition like larger than Bolza surfaces, geodesic length, it's empty. So, so this is like some empty, possibly empty sets.
Okay.
But the things that we consider when we take the border length the same as the threshold length, they're all non-empty. You can show it. And they solve the master equation. So, but there is this funny constraint, like it's like 2 sinh, 2 arcs sinh 1. Your threshold length should be smaller than this. Or if you want the quantum theory. If you want classical theory, which is like getting rid of this, it can be anything. And let me show you why this constraint is there and why it solves the master equation as a result. Like it's a proof, okay? So, the oldest trick in the book is that basically you show that one side is contain other and vice versa. So say I want to show this contains here. Well, what you do is essentially like you solve the 2 borders. The propagator collapses either in the same surface or 2 disjoint surfaces. You generate a geodesic of length L in that situation. But so they lie in the boundary possibly because now there's a geodesic in the new surface whose length is L, who's a non-contractible closed geodesic. But there is an issue. You can have like some other geodesic that transverses this this new surface. It's contained in the both surface that has a length smaller than L that can violate the systolic condition. But it turns out if you choose there's something called Kohler lemma. And that's why we use hyperbolic geometry at the end of the day. That tells you that these 2 geodesic, this one and this one, which may come back or go somewhere in the other surface, always satisfy this type of uncertainty relation. If the L is too small, delta is big, delta is small, L is big. And if you choose L to be smaller than this quantity, you can easily convince yourself delta is actually greater than L. So you want your threshold length, the length that here, to be small enough so that you don't create short geodesic when you combine surfaces. And that places the constraint here, at least for the quantum one. In classical one, there's another argument that you don't need this constraint, but the one that I'm concerned with is this. For the other side, it's actually rather easier. You say that, okay, you take a surface here, so there's at least one non-contractible closed geodesic in the surface whose length is L. Then what you do is you cut it here. You create 2 disjoint surface, which lies here, because there's it's basically some lower order surface. Or if it is like you cut open the same surface, it lies here. And that basically shows one side contain other and another contain here, as long as this is the case. So it solves the master equation.
Sorry, just to understand. So in the first thing, you said there can be a problem. Yeah. So you're trying to show that the partial VL is a superset of the right-hand side. So that means right?
Superset, what do you mean?
I mean, you have this no symbol, right?
Antibracket.
No, to the left of this figure, the collar figure.
Left. So yeah, you want to yeah. Okay.
Yes,
you subset.
this side. Yeah.
Okay.
So then you start with a point on the right-hand side, right? And you want to show that it's contained in the left-hand side.
That's correct.
So you start with the two lower surfaces whose systoles are smaller than L.
Greater than L.
So greater than L. Greater than L. And then you want to show that when you glue it, somehow the new surface should not have any short geodesics, right? Is that what you wanted to show?
That's exactly what I wanted to show. So that's essentially what I want to show. So imagine you have a...
So what if delta was too small? What would go wrong? I guess if you're saying if delta was too small, then it wouldn't be on the boundary of VL, or?
That's correct, yeah, because you see VL is defined by the all the surfaces whose systole is greater than L, right? And if I created geodesic smaller than L, then it wouldn't be on the boundary.
Not on the boundary. Okay, great. Okay, thank you.
Yeah, good question.
So you have not drawn the delta completely, right? The delta kind of closes up later.
Yeah, sure, yeah. Because the reason is that for example, delta, say that you combine two three-puncture sphere.
Yeah.
The delta could be this geodesic, but if it is like it's a torus, and you combine this, then the delta can be this one.
Okay. Yeah.
Yeah, there's a different situation. Okay. Now it's okay. This is the like the stuff that are known until 2019, and like then there, I mean it's tempting, like you have a hyperbolic surfaces, and you want to do Pence decomposition, like somebody hands you a hyperbolic surface, that's the first thing that you imagine doing. At least that's what I would imagine doing. So this was my like a dream for a while, like I tried to apply these methods of doing Pence decomposition to somehow further refine this string vertices data. So let me remind you the Pence decomposition of a Riemann this hyperbolic Riemann surfaces. So as I said, there's a metric here that I just used to define, solve the master equation, but I can still keep it there, like it's unphysical, but it doesn't affect anything. I already defined my local coordinates. Let's keep it, I can put it there. And then if you do so, then there are like this geodesics on the surface that when you cut along those geodesics, you basically construct your given surface as a with pair of Pence, which is just three-puncture sphere with three arbitrary border lengths. At least this part. So it is first of all, okay, now interactions seem to be cubic. Once you know a pair of Pence in principle, you should just combine them and construct the surface. So that was my actual talk from a year and a half ago, that I tried some bootstrap to do this, but to some success. But certainly, one can ask more, because that was kind of limited in the sense that you need to know conformal blocks, and those are only known first order, so you get stuck. But the structure is still there. So we are actually taking another approach to go with it. So let me describe this how the moduli is described in this particular way of writing Riemann surfaces. Basically, you will describe as a length of the geodesic, and the twist that it went under is basically going to give you different surfaces. So these are known, and the range are the length of the geodesic is always greater than 0, and this twist can be some real number. And these are called Fenchel-Nielsen coordinates. I will explain why these are not good coordinates soon. But the thing that I want to emphasize again is that given this type of decomposition, you might wonder if I can further factorize this VGN into these cubic parts.
Sorry, Atakan, this Zi, I thought would be angle, so it would be bounded by Li?
So not yet. I'm going to bound it eventually, but for now, I'm keeping the discussion in general.
Okay.
Because actually this gives a great like a leeway to the next point. Well, this financial Nielsen coordinates that I wrote with that range is actually good coordinates for the universal cover of the moduli space, so-called Tesch-Muller space. So in the moduli space, they are not good coordinates. They are not working globally. You know, like if you have like somewhere in the MGN and you want to work locally, yeah, they work. But otherwise, it's if you consider entire range of financial Nielsen coordinates, they cover the moduli space infinitely many times. So, you know, like that naively, it's trying to evaluate in this variables are not it cannot be done. So naively, you know, what you will think, oh, I will integrate over the geodesic length and twist, it won't work. So that's the first puzzle. The second puzzle is the systole condition. Well, you know, you see systole is, this condition is applied for all closed geodesics. So that means that if you choose a geodesic delta like this, say, gamma, I'm sorry, this gamma, and say that you take it to infinity. First of all, gamma should be greater than L, but then say that I consider what happens when gamma is really big. Like I said, when gamma gets big, any transverse geodesic should get small. So at some point, this delta that is crossing it gets small. But I know in systolic condition, this should be greater than L. So the gamma is actually also bounded above. And this also applies to all other geodesics, all closed geodesics. And in general, this is really hard because this upper bound is going to depend on the particular, like, it might be very complicated dependence on the moduli space. So implementing systolic condition is also very hard in differential Nielsen coordinates. That's the second puzzle. And the third puzzle is that how you will even do the B ghosts with this particular deformation. So I didn't go into the B ghosts like in this talk, but the B ghosts are there to basically create differential, like they're basically creating differential forms for you to integrate. And so when you feed off vectors in this P hat GN bundle, they better produce some number. And vectors in that particular bundle is associated with the moduli deformation. So you're asking, when I do this moduli deformation, which is increasing the length, what are the corresponding B ghosts? And a priori, it is not clean. Because if you do it for the like propagator, it's very clean. You know, it's like you're basically putting a propagator and that will put B0 minus B0 plus, and it will stay there. But if you increase the length, a priori, there is no guarantee that you will pick up contribution, B ghost, basically B ghost contours like dependence on all over the surface. So that's a point that I had long time like dealt with, like I didn't understand how to do it, but actually there's a way out. So the point here is that, okay, you do the moduli deformation, but how do you know that like it doesn't depend what surface that you're talking about? Okay, let me show the resolution of the first two, and then I will come to this point because this is, I mean, all of these points are very non-trivial, but all of them are actually solved. Okay, so the first point is solved by Mirzakhani. And this is really famous in physics now as well. The essential point here is that you don't evaluate the moduli integrals by themselves, but you try to evaluate recursively. And the recursion is one part of it. Another part of it is that you are adding measure factors. So basic structure is this one. Say that this stands for some integral that you want to do over moduli space. Say that you want to compute volumes of the moduli space. That's the canonical example. if you want to do it, what you do is essentially you take the surfaces like this, and you excise pants of this fashion first. That is, you take one border, L1, and you choose another border, and you choose geodesics, and you sum over the all possible borders with this factor, some kernel, and then you do this type of excision of pants.
Sorry, Atakan, in the first term, so the Li will not be there anymore on the boundaries that you have drawn on the right, extreme right?
Yes, that's correct. The Li's are
to Ln, the Li is deleted. Okay.
Yes, exactly. Good point. Yeah, sorry, like I didn't know how to eliminate the boundary, but indeed your Li's are gone. So this is, I'm not going to go into the details why this is right, but it's, you cannot, this is essentially instead of doing, like, basically what you can do is that instead of integrating once over the moduli space, you can go to the universal cover, but then you can weight your integrand. So when you sum them up, you will generate the moduli space integrand. And if you try to apply into this particular MGM context, this is you can show that this can be done recursively. So again, the most canonical example is the volumes of the moduli space in the so-called Weil-Petersson volumes. And this is defined as this wedge products of dLi and d tau I. So it's locally given by this. And globally, of course, this doesn't hold. But still, there's actually globally well-defined form. And you try to compute these volumes, and it turns out you can do it, and you can, after you choose the volume of the three-puncture sphere 1, you put into this formula here, and with these kernels, and then you generate recursive. So that's the Mirzakhani's work. And these peculiar functions are coming from the hyperbolic geometry, essentially. So this is one part of it. So, like, there is a formalism that you can do moduli integrations using Fenchel-Nielsen coordinates, even though, and the price you pay is that dealing with these functions and doing these things recursively. Okay, for me, that's solved. And the second point is that the puzzle was the systolic condition. So this is a little novel construction done by this gentlemen here. Well, you can look at those gentlemen. I don't remember their names. So they're so-called twist construction. And first, you need to notice systolic conditions are so-called mapping class group invariant. That is, when you go to the Teschmüller space, they remain the same. Systole is defined for over the universal cover. So say that I want to compute the volumes of this systolic subset that I wrote earlier. There is, I excluded this surfaces where the geodesic gets very short. So you can actually construct a recursion just between those volumes as well. So, for example, the way you can write it is that you can imagine these volumes are given by Li and the indicator function for the systolic subsets with the Weil-Petersson volume. So it turns out you can construct recursion using this function as well. And this is implemented by basically taking the Mirzakhani's previous functions and shifting them like this. So we gave us some argument, we gave it like a detailed geometric argument why this is correct in our paper. But heuristically, you can understand what's going on. You see, when I put this theta function, essentially I am cutting surfaces off. So that's essentially the idea. But I need to do it more carefully because I subtract like 2 regions, for example, with these weights. But then I actually over subtract, so I need to add something back. So this is roughly what's going on here.
Sorry,
So basically,
just getting a bit behind. So in this example, what is the symbol before VLGN? What is the written in this equation on the left-hand side?
Which one in this equation?
Yeah, what is the V before the V?
Oh, so this stands for volume. Volume of VGN, yes.
Uh-huh. And what is the notation in the under the integral sign?
So this is the integration over the systolic subset, the one I defined by this systolic condition. Curly V and L.
Okay, I see. So it's like essentially integration over the vertex region.
That's correct.
Okay.
That's correct. Another way to write it is integration over the indicator function of it.
And basically, just sorry, the message of the previous slide was that you're trying to use these Fenchel-Nielsen coordinates. The previous slide, just the Mirzakhani recursion slide with the R and D functions.
Yes.
Yeah, just above, maybe one more. Go up a little bit. Yeah, here. So here you're trying to say that basically I can do the integrals using Fenchel-Nielsen coordinates with unrestricted range.
Yes.
If I, in addition, multiply with these extra factors, these R and D factors.
Yeah, exactly. So what you need to do is that the twisting basically means instead of using this R and D, you use R tilde and D tilde. Then these things that they compute is actually compute the volumes of systolic subset rather than the entire moduli space.
So you're basically modifying the previous recursion to be restricted to this vertex region.
That's correct.
And but then there's still some R tilde, new R tilde, and D tilde.
Exactly, like the way you do it is non-trivial. Like for example, if you take this one, you will immediately see actually it kind of subtracts, put the bound L here equivalently. But the D term is rather more complicated. Even though it puts bounds on the integral, you need to add something back again with these weight factors. But yeah, and there's also still this condition. You cannot do for arbitrary L. You need to put this L star condition on it still.
L star was this 2 arcs inch of 1 or?
Yeah, the 2 arcs inch one. And again, the reason is there is a color lemma that you use to prove this. Okay, so that's the second puzzle. So there's a way to deal with the systolic, restricting the systolic regions as well. Because, you might think this is trivial, but a priori, there was no reason those systolic subsets to satisfy recursion among themselves. And that was a huge problem for us for a long time. But, by this construction, there's no problem. But these are volumes still. I will talk about amplitude soon, And before I do that, I need to describe Bigos insertions, which is kind of the technical part of this work. This is actually attempted to done by Ishibashi in this paper. And we just make the expression a little bit explicit using the hyperbolic tree vertex. So the basic idea is the following. So you want to write this, okay, I wrote Schiffer vector, but technically it's not a Schiffer vector, but basically this Bigos insertion that you need to do when you deform the length, increase the length, say, can be decomposed into 2 parts. So you have this, and you consider left pants and right pants, and you can show that the Bigos insertion that you do, given by these 2 parts. And these 2 parts are given by basically you are taking the Bigos and integrating so-called Schiffer vector. I'm not going to go into the details, but this is essentially how you implement changes on the moduli on the surface itself. And if you do this contour integral, what you will find is that there is a series of B goes insertion. So there's a B0 plus, B1 plus, and all that, which I will denote by this bat frac B. So the important point, like remember, my worry was that if I do this increase in length, I was worried about that dependence on the all surface. But the fact that this decompose and the fact that this BVIL only depends on the length of the left pant shows you that it actually depends on the pants decomposition that you do. So, it's, when you at B goes, all your concern with the pants that is bounding this geodesic and the other pants that bounding that geodesic. So in a sense, when you cut your surfaces here, the rest of the surface is still irrelevant, which is great, because like you wouldn't know this was the case. Okay, there's still this dependence on the pen, like lengths here and here, here and here, but they are not so bad, because as I talked about in Mirzakhani recursion, I'm going to do pants acquisitions anyway, so there will be some underlying pants decomposition when I do the amplitude evaluation anyway. So
what is this rho 1 in this derivative, 1 over rho 1 del rho 1 by?
Good question. So this is so-called mapping radius. So I didn't want to write this expression because it's like something involving gamma functions, and it's not looking good. So this is essentially
1 lambda 2 lambda 3, or
yeah, they depend on all lengths as well. Lambda 2, lambda 3. It has a complicated dependence though. Like, and it's how was it? It's like something like, there's some gammas. You can look at my 3-vertex paper. I don't remember to my head.
you just know it's a function. So
So Atakan, I presume the lambda 1 squared factor, so basically in the denominator, so that corresponds to a deformation parameter, right?
Yeah, the lambda 1 is that related to the length by, like, basically it's the radius now. And the way I wrote it, because this expression is easier to write in this form rather than in terms of lengths. So yeah, like lambda and the L's are related to each other by 2 pi difference.
So what is happening as you apply this Schiffer vector is, sorry, are you just changing the length, or are you actually doing some diffeomorphism using a vector field?
Yeah, so it's a diffeomorphism using a vector field. Like this is there is this deformation, and this deformation can be represented by the vector field. So that the Schiffer vector is that particular vector field.
There is some formula for the change in length under that vector.
Yeah, it is. Here I think it is given by minus dVL dLi. And the VL, the WL is basically given by how you map it here. So there are formulas. So yeah, that.
Okay, thanks. That's good.
Good. All right. So now the fun part. So these are all puzzles that has been answered. So what we did was basically put all those together and check that they play nicely. So here's the recursion for the vertices. So say that you have some string vertex with the bonds. Is there a question?
No, sorry. I mean, this was one of the deformations, the L to L plus delta Li. But what about the twist?
Yeah, that's easy. That's basically B0 minus over L2. Because it's the same as the propagator. In propagator, you also do that, and it's not that bad, right? Because twist is doesn't depend anything about the pants either.
Okay.
So that part is simple.
All right. Okay.
Okay, so here's the recursion. Well, it takes the same form with the Mirzakhani's one, but now you need to basically glue things together. And this is the hyperbolic amplitude that you compute with the border length L1, L2, and Ln. And you basically excise pants from that surface with this R and D cubic vertices. And yeah, like the basic idea is that you basically combine all of these. There's two kernels that you combine, like there's R tilde kernel and D tilde kernel. You need to combine with the hyperbolic tree vertex so that they you generate for the amplitude itself. And here there's also another feature, which is you need to consider negative length in the sense that you need to consider this B ghost insertion as well. So, because as I said, when you do this decomposition here, you need to put this B ghost insertion either on the left pant or the right pant when you decompose it. So when you, for example, do this decomposition, you need to consider B ghost insertion either here or here. So it is better to define the negative lengths as this particular way of applying B ghost insertion so that you can write the recursion in this way. But again, the way it looks is similar to Mirzakhani recursion. So there you go. You do it, then you take all the vertices, or the border lengths to be L, and that's your higher order vertex. Okay, so let me make some remarks. Well, this construction is totally background independent. No background dependence at all. So give me a CFT and I will write your recursion like this. It is stronger than BV. As I said, these VGNs were satisfying BV master equation. But what we are stating here is actually more than that. Because in that case, we were talking about this, the connection between Feynman diagrams here and the vertices here. But now actually we are relating what's interior of the string vertices. So it is stronger thanks to hyperbolic geometry. Cubic structure is manifest. Well, okay, it doesn't violate this famous no-go theorem because you see the way they relate is certainly not the way we write the cubic theory. But still, there's this very well-known structure, and it works for any quantum hyperbolic closed string field theory. Although it's kind of interesting in classical case, L can be anything, but the recursion doesn't exist for them.
Sorry, Atakan, I missed what you meant by stronger than BV. What did you draw there with the tick mark inside the V region?
Yeah, so you see, BV is all about the boundary of the string vertices, all about this condition on this this particular boundary of the chain. But this recursion, when you write this, this is actually solving the interior of the string vertices in terms of the lower one, not just boundary. So that's what I mean by the stronger than BV. Happy? Upset?
E region still exists or not? What?
What region?
The vertex region, does it still exist or?
It exists, but it is determined by the lower order vertices as well. So a priori, if you have a random string vertex, that is not the case. But in this particular case, they are also determined by the lower order vertices.
I thought this geometric master equation just has to be satisfied, right? Are you saying it's not satisfied anymore, or?
No, it is satisfied. But the geometric master equation, that was about the boundary of the string vertices. Now we are also fixing the interiors.
Oh, you're fixing the interior as well.
Yeah, exactly. So interiors are now determined by the lower order vertices as well.
Oh, I see.
Yeah, so that's the whole point, right? Now there's a relation between the cubic vertex.
I see. You're just saying that the green region is not arbitrary anymore. It's determined by the red region.
Not red region, but like a lower order vertex. Let me give you an example. Imagine you have a, you have a cubic theory, say 1, and then you have, say, 2 phi to the 4, or like, let's do the following. So you have a scalar theory phi cube, phi to the 4, phi to the 5th, etc. Okay, well, you can say they are recursively determined. Okay, it's a stupid example, but you can say it. So it is like that, like say that you have a right theory. If your cubic vertex is like coefficient is 1, then all the rest of the coefficient is 1, or the next coefficient is 1. So it determines each vertex is recursively, right? So that's what I mean here, if that makes any sense.
Basically, you're saying that the only input you roughly need is like the 3-point vertex, and then by these recursion integrals, you can get the green region of the higher order diagrams.
That's correct. That's precisely what I'm telling you.
I see.
Yeah, you can also look at my Stubbs papers with Hederler. That has like a toy model that is like more familiar. But this is like its hyperbolic version in certain sense. Okay, let me reap some benefits. Okay, so let me. Is there any other question about this, by the way? So this is the main result of this paper. Basically, you can, the cubic data is all you need, and you need to run some Mirzakhani recursion type of argument to determine the higher orders. That's the whole paper is about. Okay, let me talk about implications. Well, one implication is that there's this like funny structure that you can recast in recursion relation. So say that first you define this partition function as a basically, string vertices, but you also integrate over the length L. So this is some formal partition function, but for a better lack of a name. And then you define the differential operators like this. So there's a first order derivative with respect to string fields. So there's this A. So this is defined by the cubic vertex. And there's B. This is going to be related to R. And this is going to be related to B. So this is just renaming. Like I have vertices. Now I'm defining products based on that, like what we usually do in string field theory. And then D here is that the V11, one puncture torus. So basically, this is like some differential operator. You see, like there is a first order derivative, quadratic term. There is also like derivative and a quadratic term, and the second order derivative. And you can basically write the recursion as this differential equation. So if you're familiar with this so-called Witten's conjecture, is basically the same idea. So, well,
the definition of psi of n. What was the definition?
The psi
of this kind of psi of L. What's the
So it's an element of the Hilbert space. So this is element of the level matched Hilbert space of 2D CFD cross the dependence on some length R. So this is like some set of string fields, like they're parameterized by a number.
And what is Z of that?
So it's a partition function. Yes.
So you mean a wave function or what? Sorry.
So like say that I'm giving it some arbitrary state in the Hilbert space with this dependence on the length. So I take that one and I basically feed into the vertices, and then I do the integration over the border length. Is that so? Basically, this is some scalar now. Good. I mean, I cannot see, so I cannot tell like if whether you're on board or not.
I'm just asking about the just the name. I mean, the partition function usually doesn't depend on an argument, right? It depends on some.
Well,
function, you don't have any external insertions. That's what.
Well, okay, that's why it's like in the quotation mark, because it's some
like the string wave function or something. This is what people would call the string wave function.
I'm not sure. Again, like you shouldn't take it this literally. It's just some function of this particular string field. That's the extent of it. Usually in this literature, like this quantum air structure that I will mention next, people call this a partition function. So that's why we call it partition function.
Okay.
It's a nomenclature, nothing deep really. It's just you are given a string field that is like parameterized by some length L, and then this gives you some number, in terms of those fields.
Roughly speaking, this boxed equation is somewhat like the Schrodinger equation for that, or?
Yeah, I mean you can tell that because this is a second order. So yeah, that's fair to say that. I mean, if you want to call wave function, I'm also okay with that. Okay, so well, the point here is that the recursion is equivalent to this. And if you solve this equation order by ordering kappa and h bar, you'll generate the hyperbolic string vertices. So you might imagine that there's an underlying feature that gives you this equation. And then if you try to solve perturbative, closed string field theory is what you get. So that's one speculation. And again, there is this quantum air structures, which is some way to encode topological recursion. And this is a question, like I don't know the answer. Like maybe that's a one way to understand this recursion in a nice way. And considering this equation and considering genuine solutions, you generate something non-perturbative. So that's kind of like speculation, but certainly structures are extremely similar. So that's one implication. This is a nice way to write it. Maybe there's a deeper facts about it. Just putting there. But then the second, more impactful for me is that this recursion constrains the solutions quite a lot. So say that I define this particular string field the following way. Basically, I take a solution to closed string field theory equation of motion. Say that I know it already, and I take it, and I basically feed it, like define these products. I take the solution, put it here, generate the state, and I do the tree one as well. So the classical solutions, and I do the for all of them, and define the string field phi L1 is what I will get at the output. So here the border length that I choose is L1. But where I insert the genuine solution is our L. And their systole condition is still L. Well, one trivial thing to observe is when you take L1 to L, set this border length to L, since psi tilde is a solution to the equation of motion, it should give you the minus cubic psi. Because when you do that, the whole thing is actually 0. And say that you gauge fix, then you generate this relation. So why am I telling this? Because if you define this phi field, you can recollect this equation of motion in the following way. So I'm not going to derive this, but essentially you take the recursion and you are just realizing that I can have a phi of L1. I have this thing as well, and like basically the rest of it is coming recursively. So the phi of L, the thing that I generate here, actually can be thought as a part of it here. Like this is like essentially the recursion for Catalan trees. Like if you're a binary tree of some sort, then you can imagine, you can construct the next order binary tree by attaching this or attaching that. So this gives you some constraint integral equation. Again, like the easiest way to show it through that differential constraint that I showed you, but it's not a hard computation. But the thing that the cubic vertices are here is R, and here's D, and it's an integral equation. So this is if you can solve this equation, if you can find phi of L, phi of L1, then you just set L1 equals to L, like here, and you apply the beta, and you get the solution. And that's it. So, I mean, okay, you can say this is like cubic equation of motion. I mean, I didn't want to say that, but certainly this is some condition according to it should get satisfied. So you can we show that this similar equation also works for this paper with Ted Earler that we wrote last year about the stop theories, which has a similar structure, and it satisfies a similar equation, and combined with some guesswork, you can actually generate the solution just by looking at this equation. So certainly we know this equation contains some data about it. You can also generate the fluctuations around that non-perturbative vacuum. Okay. So are there any questions about this? I was a little bit quick about this, but certainly this is I think the most interesting result of this paper.
I think you can continue.
Okay. Yeah, because nobody's video is like on, so I cannot tell like if you're happy or not. Anyway, so let me summarize. So there are two results. Well, first one, we showed some topological recursion between vertices of hyperbolic string field theory. So if you know the generalized hyperbolic tree vertex plus this Mirzakhani kernels with twisted in certain way, you can generate all higher interactions in principle. That's the first thing that we showed. The second thing we showed is that this structure in particular implies a certain quadratic integral equation for closed string field theory solutions. So, well, these are the two results. And the future work for me is the following. Well, of course, the point of this was the constructing genuine non-perturbative closed string field theory solutions. And I want to say work in progress, but I don't want to get anybody's hopes up. But there are certain ideas that I'm trying, and they are kind of like giving positive results. So certainly it can work, but it's like a big question mark still. And so the tachyon vacuum is the one that I'm after in particular. And maybe sense third conjecture for closed strings. The fact that like in this tachyon vacuum, there is no perturbative excitations. That will be certainly a very neat thing to prove. Another thing is that this, as I emphasize, the origin of this constraint. So is there like a deeper meaning to it in this context that I am not particularly sure yet? And the third thing is obviously like you can consider extension. You can say, let's do open hyperbolic and see how Witten's theory relates to it. For example, open closed ones, large N ones, supersymmetric ones if you're really ambitious. So certainly like this recursive structure, if you choose vertices based on hyperbolic geometry, should generalize to those cases as well. So this is the what I plan to do, especially this one. And hopefully, next time I give a talk here, I talk about that one. But we'll see. Anyway, thanks for listening.
Thanks a lot, Atakan.
Yeah, thank you. I can take more questions. There are any?
I have a very naive question. I'm not really familiar with this work. By solutions to this closed string field theory, do you mean solutions to this geometric mastery equation that you talked about at the beginning? Is that
No. So, well, I already solved the geometric mastery equation. This is the thing that I said in the first slide. I'm sorry, this wasn't clear. Okay, this is not. Let me go there. So solutions of string field theories of this form.
I see, okay.
Yeah, you see, like if you ignore interactions, basically solutions means that your QB closed states, one graviton or something like that. But then the like interactions are basically deforming it. And you know, this is basically solving the equation of motion of the field theory.
Okay, yeah, thank you.
Yeah.
Are there any more questions from the online members?
We had a lot of questions already during the thing, but this was very clear, Atakan. Thanks.
Yeah, okay, thank you. I hope it was, I communicated the idea.
So this delta, I just have one maybe final question. This equation with two derivatives on delta psi or something, in the end, you had this d dot z equation.
Yeah.
You know, like there was this paper by John McGreevy and Nabil Iqbal. They were trying to study theories of strings as effective theories, like, you know, imagine some confining theory, you have some effective string. And they were basically trying to write down, you know, some area derivative. So the wave function is a function of some loop, right? Like the string is like a loop. So for them, like the wave equation is like a loop. And the differential operator that they act was kind of like an area derivative. So you sort of deform the loop a little bit. So its area sort of enclosed by it increases by a little bit, and kind of some version of that had these double derivative. So basically what I'm asking is there some kind of semi-classical limit of this equation where, you know, like the string tension is very large, let's say. So that would be the case for them where the string tension is very big and
well,
it's a vague question. First of all, I'm not even sure these are related, but it is.
I mean, if the string tension is really large, then you are in the long wavelength limit, no? So, so that will basically be just word lines.
Yeah, but the point is like the expectation value of some loop will be like area law, right?
I see. Well,
okay.
I am not particularly sure. So the derivative here actually have a very particular meaning in this context. So, but certainly what you said is like actually interesting because, you know, maybe like this equation's natural taking place as some loop space of your target space-time. And I mean, that will be natural for me. And in that context, maybe you will get areas and whatnot that this loop surrounds.
Yeah.
But it's not immediately obvious to me how you can do this.
I mean, I think their considerations were kind of simple, that if you just start with some theory of wave functions on loop space, what are the kind of, you know, Schrodinger type equations you can write down?
Yeah, I am familiar with that work, although it was some time ago.
Okay.
All right.
Yeah. Thanks again. Thank you for giving a talk so late.
No, it's fine. No. I enjoyed it.
Yeah, this was fun.
Right.
Okay, good night. Have a good night. Yeah, see you. Bye.
Thank you. You have a good rest of your day. Take care.